Testing, testing, 1, 2, 3. Good afternoon, fancy meat computers. How's everybody doing today? It was kind of rainy this morning, but now it looks like it might turn out to be a decent day after all. So we're having a poll right now to ascertain. I might have thought to take this poll prior to having set Project 1 and the due date for Project 1. So I guess there are a lot of people in this class who are doing a minor in computer science and who never actually took 1JC3, judging by the polling numbers. We've got 27 out of something like 120 votes reporting, and it looks like the percentage of the class who has no idea what Haskell even is hovering around 40%. Well, I guess that's a little bit awkward. I had kind of assumed that you guys knew some functional programming, and it seems like you might not, a lot of you, and that is going to be problematic because the assignments as written require it, or at least the first project does, and there's a bit of it on assignment 2. So I'm going to very, very, very strongly recommend attending tutorials from now on if you're a person who is not as familiar with Haskell as you might otherwise have been if you had taken 1JC3. I assume that the split here is people who took 1JC3 and people who did not. If you took 1JC3 and you still don't know what a Haskell is, then you probably, my sympathy is somewhat less. But, oh my god, it's coming up to like 50% of the class doesn't know Haskell. I think that Project 1 might be getting an extension. By the way, this isn't vote on whether you want an extension on Project 1. This is like, please answer truthfully to this, because this is basically going to dictate what the tutorials look like for probably the next 2 or 3 weeks at least. Oh my god, more than half the class doesn't know Haskell? It's been a really long time since you touched Haskell. Even those of us with 1JC3 are relearning a lot. Yeah. Well, 1JC3 is like, it's a bit notorious for its reputation for being difficult, so. Grumble, grumble, grumble. Grumble, 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 grumble. This is okay. We're just gonna have to figure it out. It'll be fine. By the way, when you guys took 1JC3, those of you who did you have for it? Was it Curtis, or was it, I think Dr. Farmer sometimes teaches it? So, okay. Dr. Farmer? Okay. So, if you're wondering what it looks like when your professor is dying inside, this is what it looks like when your professor is dying inside. He did not care for the coding aspect of it at all. Curtis is a TA. Alright, we're going to put together some resources for you guys. Okay. Alright. Alright, well, it is what it is. Before we, okay. So, before I put everybody in the position where, you know, it's now necessary that we should take a brief detour in our studies in order to learn us a Haskell for great good, I should justify why we should learn Haskell. So, functional programming, there's stuff that you can do with it that's, like, out of the way, I'm going to say, in other programming languages. Obviously, functional programming is still, like, Turing complete and everything like that. So, you know, it is possible to implement in any language, any program in any other language. That's how programming languages work. But with respect to functional programming languages in particular, the semantic of these languages has been set out so that it is much easier to translate the kind of stuff we're doing, you know, in this, there we go, in the slides right here, right? The stuff that we're covering in the slides translates very easily into a functional language because this is the design, like this is the purpose of functional languages from a design perspective, is to support this type of high-level mathematics. So it's unfortunate that you guys didn't get, you know, that you got, like, it sounds like a taste of Haskell in first year and then haven't touched it since, because it would be super, super useful in order to, it would be super, super useful for you guys to know functional languages right now. So, I received various comments at the beginning of this course about why I decided to move away from the, you know, this course as a language survey course and into this course as a math course. So I guess we're going to be moving it back into the let's learn a language folks territory. I'm not sure the degree to which I'm going to use lecture time for this. I hope we might be able to get away with it in the context of tutorials, and I think a certain amount of self-study might be necessary. We'll see how it goes. Like, the problem, of course, is that, like, we've got shit to cover, and I can't spend all of my time reviewing 1JC3, you know? For those of you who never took 1JC3, I have, you know, it's just, it's rough, you know? It's just rough. Yeah, so I'm receiving a suggestion. Prioritize the TAs for a primer on Haskell, for those who don't know or don't remember. Yes. Yeah, that's what we're going to end up doing. Also, apparently, the TAs are also aware of this problem, and they've been throwing some resources at me, so there's apparently Curtis did a series of short videos that are like a Haskell primer, which are reportedly very good. So we'll distribute that information as well. I'm not sure how long or how many of them. I haven't had time to watch them or anything. So, you know, the curriculum will be released as I have time to, you know, dig my way through it. make sure that it is, what we need to know and that type of thing. Maybe know what to recommend you watch and what to recommend you don't watch if there's anything that isn't relevant. Because, I don't want to waste your time. But yeah, so we're going to do my plan at the moment is see what extra resources I can dig up to recommend to you guys for self-study, and basically bend the overwhelming majority of the tutorial time to be teaching you guys Haskell. Haskell programming is almost trivial to learn. Knowing enough to do the project is the problem. Well, for those of you who... so, Haskell gets very complicated at the deep end of it. As your colleague points out, the simple stuff to learn in Haskell is not... It's like if you already are a decent programmer, it won't take you too long to pick up Haskell. It's definitely a very different way of thinking about programming, but it shouldn't take you too long to pick up the rudimentary basics of Haskell. The question is how much math do you need to do Project 1? And I can tell you that I have myself implemented Project 1 using only basic constructs in Haskell. So, for me, if you know the data type, the creating data type stuff that's being covered this week in tutorial, plus being able to make functions, plus having a good handle on pattern matching, and understanding the correspondence between that and our rules of inference that we're going to be talking about when we get into the semantic side of things with respect to untyped arithmetic expressions, then that you don't need high-level Haskell skills to be able to complete the project. This is what I'm trying to say. Although high-level Haskell skills will be useful, just like being an expert in C before you take a C course would make you do really well in that C course, but yeah, well, it's it's gonna be a nip and a tuck operation, right? Some people were hoping to see more examples of the types of proofs and things that we would do during lecture and that appear on the assignments. Some people were hoping to see more of that in tutorial, but I think at this point, so much for that. At least until we get you guys up and functional, so to speak. So, Mariddle just posted a link to Dr. Farmer's 1JC3 lectures. If it's all of the lectures for an entire course, that's going to be on the order of 50 hours of viewing time, which is too much. I'll see if maybe those we'll throw those in too. But I think what you guys need is a quick start guide, not a whole course on it. So, yeah. So more people don't know Haskell than do. Lovely. Oh, is that the Curtis playlist? Did you find it? I'm not gonna open it right now. I'll sort it out after class. Yeah. Yeah, this is exactly what I'm saying. Yeah, we'll post some links to some videos. Make sure they're short enough to be digestible, and we'll make sure the links work. Okay? Okay. So, that brings us into our announcements for today. At 15 minutes into the lecture. So, number 1, there's been a request for computer science representatives. So the Computer Science Society wants some representatives. If you're interested in fulfilling such a role, please fill out one of the following forms that are linked. if you don't know what a class rep does, they organize fun events and like generally represent the class. Basically your job is to be a politician. So if you like politics, then here's your avenue. So I've posted the topic 4 slides. I corrected a typo on assignment. Testing, testing, 1, 2, 3, testing, testing. Testing, testing. I wonder what the hell happened there. Am I coming through? Stream dead. Yes, yes, yes. Yeah. Okay, well, I don't know why, but my computer crashed. Like a hard crash, right to being off. I don't know what it was. I don't think there's a button on my keyboard which turns my computer off. So, and it was like a reset. I don't know. I don't know what just went on there. But let's hope it doesn't happen again. But yeah, so that's how fast my computer reboots. If any of you are interested in how fast the professor's computer would reboot, that's how fast. There we go. Hey. So, yes, what was I talking about? Yeah, okay. So, back to base. Yes. If any of you ever wondered why Linux, there you go. So, this kind of, I've been talking about the whole like half the class doesn't know Haskell thing, but this is also like an interesting development in the course of like how the course is developing in general, because at one point I wasn't convinced that we would do projects. I thought that we would just do assignments, and that I would like take the things that I was going to make into projects and like do them as assignment material, because it wouldn't be big enough to be, you know, it wouldn't be big enough to be, its own thing. But I've decided, as I'm going through the course material, I've decided that it actually would be an extremely valuable exercise for you guys to actually do an implementation of these languages that we're learning. So, yeah, that's what we're doing. Unpopular opinion: Windows is the objectively superior operating system. Okay, but in an imperative or a functional sense, it's Linux. So, this is quickly developing into your heaviest course load this semester. We'll try to keep that under control. Yeah, because the other thing is I can't destroy you guys either. So, you guys are taking other courses, but I didn't, like, honestly, the, like, if I were to sit down and program Project 1 myself, it would probably take me about a half an hour, maybe. But I already know Haskell. That's the thing. Okay. I'll try to, okay. Your input has been registered. Your input has been registered. Yeah. So, anyway. All right. Well, like assignment 1 took 8 hours? Let me do something here. Because apparently this is the lecture today, is asking people how the course is going. How long did A1 take you? Less than 2 hours. Between 2 and 4. Between 4 and 6. Between greater than 6. Okay. Well, I can't really do anything about A2 because it's already been released. Yeah. Alright. Okay. Will there be an answer key for assignment 1? Normally, I would use tutorials to have the TAs go through assignment 1, but yeah, you do need Haskell for assignment 2, one of the questions on it. I put material in the tutorials this week that should help a lot with that question on the assignment. So if you go to tutorial, you should get a pretty good head start on it. All right. We need to actually do some compute. Like we need to continue on with the lectures now. Because, you know, half the class is now gone. So. Alright. So, if you remember, last time, we were defining the syntax for untyped arithmetic expressions in various ways. We had our rules of inference, or our inductive definition. We had a slight rephrasing of that as rules of inference. And then we also had our constructive definition. So, what we're interested now is proving that... Wait, did we already do this? Yeah, weren't we on to induction? I think we're on induction, right? Yeah. Yeah, we're on induction. Okay. All right. So, induction then. Ugh. Yeah, okay, good. So, induction on terms then. Induction is the glory of science and the scandal of philosophy. So, depth and size. To facilitate our current and future languages, it will be useful to define the concepts of depth, and size as they pertain to terms, right? The depth of a term is analogous to the depth of a tree. It really is a very useful model to have in your brain that terms are trees, right? So, you have an if statement, and there are 3 terms contained within that if statement. That's like a node in a tree that has 3 branches, right? If you have a plus, if you have an addition, that has 2 subterms, x plus y. X is its own term, and y is its own term. So that's a tree with 2 branches. Like, trees are the model data structure that you should be using in your brain for analogies. So, the depth of a term is analogous to the depth of a tree. It is the longest path from our starting term to a terminal constant. Of all of the terminal constants you have in a particular expression, they may be at various depths, but the depth of the term itself is the longest of those. Continuing the tree analogy, the size of a term is the number of nodes in the tree. Here, a node is any of the terms described by our grammar. So, ifs are a node, true is a node, successor, predecessor, all nodes. In addition, it will be particularly useful to be able to extract the set of constants used in any particular term, which is actually the simplest of these and has nothing to do with induction, but we'll need the definition later. So, this is how you define the set of constants. The set of constants appearing in a term t, written consts t, is written as follows. True, false, and 0 all are just a set containing true, false, and 0. Constants of successor, predecessor, and is 0 are just the constants of the subterm, so they don't really contribute anything themselves. If you have successor of 0, then the consts over that would just give you 0. And consts if then else is the constants of t1 unioned with the constants of t2 unioned with the constants of t3. Remember, the union operator does not include duplicates, so it would be very easy then to get a set of constants that included all 3 of these. So there you go. Constants. Size. The size of a term t, written size t, is written as follows. All of our sort of value terms, true, false, and 0, have a size of 1. Our sort of unary terms, unary functions, successor, predecessor, and is 0, increase the size of whatever the size of t1 is by 1. And in the case of if then else, it's the size of the first term plus the size of the second term plus the size of the third term plus 1. So you can see that's just a sum of all of the things there are in a term, right? And then, of course, we have depth. the depth of the term t is written depth t and is written as follows. The depth of true, false, and 0 is 1. The depth of one of the unary functions is whatever the depth is of the subterm, plus 1. And interestingly, if then else, the depth of that is the maximum of the depth of any of the subterms, plus 1. So this is kind of interesting because we haven't done a formal definition for what the maximum of something is. But, hopefully our intuitions are sufficient for us to understand what the maximum of 3 numbers is. So, with these new definitions, we can now introduce 3 exciting new forms of induction. We can perform induction on size and on depth. So, for size, the argument basically goes like this. If for some term in Ts, given the predicate r for all r such that the size of r is less than the size of s, we can show that Ps. So basically, what induction on size does is it allows you to build up an inductive argument on the size of the terms themselves. There's some discussion going on in the chat right now about how long someone's solution is relative to the number of marks they're going to get. And I'm going to tell you right now that you don't have to write pages and pages to get a mark on assignment 1. The proofs in assignment 1 were not a couple of paragraphs would have done kind of sort of deal. It's like there is such a thing as going on too long about it too, there's a balancing act between not saying enough and saying too much. You should limit yourself to those facts which are relevant about the case at hand. But yes. Well, we're gonna have a fun time. The TAs are going to be getting your marks back to you within a week, so you should get your feedback reasonably quickly on them. So that's induction on size. It's like, in the case of the natural numbers, we build things up from 0 all the way up to whatever number we want to do, and this is analogous to that, but we're operating over the size of a term. Depth is a very similar idea, except rather than doing induction on the raw size of the term, it's the level that you're at in the tree. So yeah, basically, these 2 forms of induction are derived from complete induction over the natural numbers. Now we get to structural induction over terms. So we talked about structural induction, and now we have terms which are a structure, so we can do structural induction over terms. For S, an element of T, we can show, if we can show that some predicate holds for the language constants, and given PR for all immediate terms of subterms of R, given P of R for all immediate subterms R of S, I think that of is extraneous, we can show P of S, then we may conclude for all S in T, P of S. So this is induction again, but it's, we're doing it structurally, but the structure is the terms. So we're concerned about what the possible subterms are, what the possible next terms are, this type of thing. These methods of induction are equivalent to each other, but using one or the other can simplify our proofs. In general, we have a preference for whichever form of induction makes the proof the easiest and simplest. It's kind of like, if you're hammering in a nail, you could use a screwdriver or you could use a hammer, right? Formally, these three forms of induction are interderivable, so you can derive them from each other. As a matter of style, we will often use structural induction because A, it's a bit more intuitive, and B, it avoids us having to detour into numbers, which, you know, just complicate the issue. So, in general, proofs in the above style will have the following structure. We are given a term T and a property P. We assume P holds for all subterms of T, then we break the proof into cases. Our goal is to demonstrate P of T for each possible subterm. Since languages can have a lot of terms, we will often only create proofs explicitly for the interesting cases. What constitutes an uninteresting case will become more obvious as we progress through the course, but this will be sufficient to complete the proof. So, you know, very often, for example, say you have your constant values, right? Your values in your language. It may be that the particular property that you're trying to demonstrate is completely facile for constants, right? Like, you know, any subterm of this term has to be a 3. Well, if it's a constant, it doesn't have any subterms. So there you go, you know? That's just a silly, off the top of my head example, but you don't have to go through each individual constant and make the same, like type the same sentence like 50 gazillion times. It's sufficient to say it once for this constant and say, and the rest of the constants hold by the same logic, and then that's sufficient for that part of the proof. So, good. That's it. If you want to read that comic, I'll blow it up a little. If you want to read this comic, pause the video, but if not, we're going to be moving along. Are there any questions about that before we move on to topic 4? Give me a thumbs up if you don't have any questions. Like, just to the question of, like, okay. So, just to the question of, like, how much detail we're expecting on these assignments. Like, you guys are undergraduates, so, like, we're not expecting graduate-level responses from undergraduates, okay? So, it's like, okay, sure, but what does that mean? It's like, I don't know. You'll have to submit something and find out, you know? Fortunately, with 10 assignments and them only being worth 30%, it's like they aren't, each assignment isn't a huge amount of your final grade, so you have some wiggle room and still get your A's. But, so, topic 4, operational semantics. So, semantics. We all know what semantics are. Semantics as opposed to syntax. Syntax is the grammar of the language. It's how the language is written. Semantics is the meaning of the language. It's what the individual elements of the language mean, what they perform, what is their mode of actuation. So, in the last topic, we examined various strategies for formally specifying language syntax. By specifying the semantics of our untyped arithmetic expressions language, we will have a complete and working model of a programming language that's ready for implementation. Footnote. By you, during an assignment. Actually, during Project 1. There are in general, 3 major semantic styles, but we're only going to be using one of them. So there's operational semantics, which is first because that's the one we're using. There's denotational semantics, and there's axiomatic semantics. So let's talk about operational semantics. The underlying semantics, under the semantics, under operational semantics, we define how a language behaves by specifying an abstract machine for it. An abstract machine is abstract because it operates on the terms of the language itself. This is in contrast to a regular machine, which must first translate the terms to instructions in the computer processor's instruction set. So, what an abstract machine is kind of like a concept like a Turing machine, right? Like the Turing machine is an abstract machine, right? It's a conceptual machine. It has a state, and it has rules by which it transforms that state into other states. That is the essential, like that's it. That's everything. That's what operational semantics is composed of. It's like you have your definition of terms, and you have rules for transforming terms into other terms. And the thing that executes those rules is a conceptual mechanism called an abstract machine. For simple languages, such as UAE, the state of this abstract machine is simply a term of the language. As things get more complicated, this might change, but for now, the state of the machine is just a term. The machine's behavior is specified by a transition function. We're going to be calling it a relation, actually, most of it, or an evaluation relation or a transition function. The meaning of a term is the final state of the abstract machine at the point of halting. So, you have a term, right? Like, for example, is 0 successor predecessor 0? That would come out to be true. So, the meaning, the semantic of that term is true. Because that's what the abstract machine would eventually evaluate that expression to, right? So, in operational semantics, you, in general, have 2 styles. You've got small step semantics and you've got big step semantics. We're going to be examining the differences between these two a little bit later on. But essentially, the small step semantics, they give you a single simplification, and the idea is that you would then run them together until it stops changing. So the small step semantics tell you how to get from one term to the next term in a chain of derivations that eventually results in the final answer. All it does is specifies one step. That's why it's called small step semantics. Big step semantics, on the other hand, specify it in terms of its final result. So, again, we're going to see this a little bit later on, but rather than taking one baby step a number of times rapidly, the big step semantics take giant steps all the way from, all the way from the top to the bottom all at once. So, yeah, basically. Sometimes we will use 2 different operational semantics for the same language. For example, one might be abstract on the terms of the language as used by a programmer, and the other might represent the structures used by the compiler/interpreter. One might even be, you might specify operational semantics in terms of the machine language that the CPU will eventually use to execute things. This would, in the case of having these 2 different semantics, proving a correspondence between these 2 machines is equivalent to proving the correctness of an implementation of the language, i.e. proving the correctness of the compiler itself. So this is how you prove the correctness of a compiler. You have an abstract machine which operates on the terms of the language. You have another machine that operates on the actual instructions as executed on the CPU, and you prove that the two are equivalent and that they do the same thing. And that proves that the language is being implemented correctly. So there you go. Denotational semantics. So this is a different approach to semantics altogether. Rather than viewing meaning as a sequence of machine states, under denotational semantics, the meaning of a term is taken to be a mathematical object, such as a function or a number or an element of a set. We need two things. Number one, we need semantic domains, a collection of sets of mathematical objects which we can map terms to. Interpretation function, a mapping between the terms of our language and the elements of our semantic domains. So, consider just for instance, successor, successor, successor 3, right? We think of this as being equivalent to the natural number 3. In reality, there's no such correspondence. That correspondence exists because we are applying a concept of denotational semantics to our language, where that may or may not be, in the case of the successor function, it's useful to think about it that way. So that's a useful tool for learning what untyped arithmetic expressions do. But this is a different style of semantics than operational semantics. The two sort of cross-pollinate at certain points in history, but they are distinct styles. So, yes. So, in this case, in the case of something like successor, successor, successor 3, the natural numbers are the semantic domain, and the interpretation function maps terms of UAE to n, nominally by counting the number of successor invocations. So, notice that semantic domain is plural here. It is entirely correct and possible for your programming. Any fully fledged programming language is going to have many semantic domains, not least of which would be the integers, the real numbers, and, Boolean truth values, just for a start. So, you're allowed to have multiple semantic domains, but what you really need is a way of mapping terms into it. The search for semantic domains to model language features is an area of computer science research known as domain theory, and is especially applicable to functional programming languages. Denotational semantics have a number of advantages. Number one, it avoids messy implementation details. 2. Properties of the semantic domains can be used to reason about program behavior. For example, proving two programs have the same behavior. So, properties of the semantic domains can be used to reason about program behaviors. So, if you have multiple things that map to the same thing within a particular semantic domain, that's a property, and you can use that property to prove things, right? You can do things like proving two programs have the same behavior. You can do things like prove that a for loop in C does the same thing as a while loop in C. Proving a program meets some specification. Proving that certain behaviors are impossible, be they desirable or undesirable. So I think that's it for today. We'll do axiomatic semantics next time. But yeah. So I know it's kind of dicey because I'm asking you to trust me, but please just trust me that I won't try to destroy you with this course. If I destroy you with this course, it will be unintentional. But I'll put some time. I'll allocate some time together today to sorting out your the little Haskell problem that we have today and various other things. Also, if there are any questions, I'll take those questions now. Such devastation was not my intention. Yeah. Ah, that's a good question. So, for assignment 2, question 4, when I say unary function, what do I mean? What are the expected inputs and outputs? There are no expected inputs. It's just like, okay. All right, I'm going to do a little tiny bit of Haskell for you guys. Just a tiny bit of Haskell today. Get it. Example.hs. So in Haskell, if you've got like a unary function, it would look something like myfunc int myfunc is equal to 6. That's what I'm looking at. It's a unary function. It is a function over, like, that's it. That's what I want. Put a term there and make sure that it's labeled with whatever name you give the type. Yeah. Well, I'm like, when I say unary function, it's like, it's a function from this. It would be like f is a subset of s. It's actually kind of more like a predicate, the way that we defined predicates this time around, but. Well, it's not like it's. Yeah, you can think of it as like a term literal. Yeah. Would quotations suffice for EBNF concatenation or commas? Or space, like EBNF concatenation. Whatever convention you choose to use for EBNF for concatenation, or whatever syntax you use for EBNF, I don't care, so long as it's used consistently within your work. So if, like, Wikipedia has a slightly different way of going about it than I put down in the slides. If you want to use the conventions that are in Wikipedia, do it. Just do it consistently. Just do it consistently, okay? Yeah, you can't compile the A2 text file because it doesn't contain, like, I didn't give you the image file that's contained in it, and I don't know why you would need to compile it. You can just get the PDF version. Haskell doesn't have variables, it only has functions. Hello, Python has reserved keywords that we cannot use as identifiers. Do we have to take that into account when designing the grammar? Yes, but Haskell also has keywords, and you should not use any of them. I state something like that in the assignment itself. It's like, true is already used in Haskell, so you're going to have to name true something slightly different in order for it to work. Yep. Any other questions? Um, Moonstar, you're overthinking the assignment. I don't know how. I'd have to look up how to do EBNF exclusion. Yeah, you're making the problem harder than it needs to be. So when I said, you know, like decide what is or is not an identifier, all I'm looking for is the rules of like the characters that are valid identifiers. That's it. I'm not interested in like exclusion from keywords and that sort of thing. Like, I think that possibly the problem with these assignments is that people are making them harder than I intended them to be. By being more thorough than is required. In Project 1, Step 1, do I mean both Boolean values and numeric values? Let me take a look, and I'll tell you once I look at the thing. Let me take a look. There we go. Yeah, this definitely assumes you've done assignment 2 first. Yeah. Yeah, so, yes. Yeah, you need to start by creating that. Like, so as we go on in topic 4, you'll see that, like, when... Oh, that was supposed to be a joke. I'm sorry. That, So when we get into, like, the arithmetic, the extended UAE semantics, they've broken the terms down into, like, Boolean values and numeric values, roughly speaking. And so as opposed to, like, for this we're going to start off dealing with just Booleans, and we're going to do just Booleans for most of this, and then at the end we introduce the rest of the rules and basically say, yeah, and a lot, like, the properties we've been discussing still hold. So yeah, we distinguish between numeric values and Boolean values by putting them in different sets. Yeah, if it, like, yeah, the difference is not large. That was, yeah. Yeah, the difference is not large between the two of them. This is what I'm saying, is like, I really intend, like, a lot of these to be like softball questions, you know? Like, the sentence should be Boolean and numeric values. Let me see here. P1. Yeah, Boolean values and numeric values. In the, like, in the slides, it doesn't say Boolean values, it just calls them values and numeric values. But, like, I make the distinction, well, it's a set of values, and the only values in there are booleans, so it's a set of boolean values. But that distinction actually isn't made by the textbook. But yeah. Anyway, I'm gonna log off here. Thank you very much, folks, for sticking around for it. Peace.